Goedemiddag allemaal. Welkom bij het webinar Kansen bij het ontwerp van machines en gereedschappen. Fijn dat jullie er allemaal zijn. Mijn naam is Lucel Mulder, ik ben marketeer bij Layertec en ik mag het webinar van vandaag voorzitten. Good afternoon to all of you. Welcome to the webinar, Opportunities in Machine and Tool Design. I am glad you are all here. My name is Lucel Mulder, I'm a marketeer at Layertec and I have the pleasure to kick off this webinar. Today we have two guest speakers from Desktop Metal. That's why we will present this webinar in English. The main speaker is Kirk Dyke. He is a senior application engineer at Desktop Metal. He is joined by Jeffrey Paquette, also an application engineer, who will take care of the Q&A at the end of the webinar. I'm really happy that Kirk and Jeff are with us today. I know they have great experience in all technical aspects of 3D metal printing, and they will share lots of examples today about the opportunities of 3D metal printing for machine and tool design. First of all, some logistics. You are all muted when you joined the webinar, but if you have any questions, please use the questions box in the GoToWebinar panel. The webinar itself will be recorded, and I will share the recording tomorrow together with the slides. And lastly, there will be a survey popping up when the webinar ends, and we are very much looking forward to your feedback. Okay, let's start with a quick introduction of Layertec. Layertec is part of the Visitive Group, serving more than 18,000 companies worldwide. We are listed on the stock exchange with the name Alviv, and if I could point out one thing, that would be that we are always heavily investing in our R&D. And when we zoom in on the Benelux, then you will see three companies in the market. Design Solutions, reseller of SolidWorks since 1998. We have Visitive with the entire portfolio from CAD, CAM up to Katia and Innovia. And of course the 3D Experience platform. And there we are. Layertec, we are a reseller of Formap's, Ultimaker and Desktop Metal 3D printers. We are thus enabling companies to print in plastics, in composites and metal. And with all our services combined, we are truly a 3D printing partner for more than 200 companies and professionals in the Benelux at the moment. All right, without further ado, I would like to hand it over to Kirk for the next 40-45 minutes. Kirk, I will switch over the presenter role right now, and then you can start the presentation.
Okay, no problem.
There you go.
Okay, is everything viewing okay, Lisa?
Yeah, looks okay. Perfect.
Fantastic, thank you. Right, good afternoon, everybody. As I've been very well introduced, my name's Kirk Dyke. I'm a senior applications engineer for Desktop Metal with a number of decades of 3D printing, metal printing, plastic printing, etc. Here to share some of our knowledge with Desktop and give you an overview of how our systems work. Okay. So, as you know, Desktop was founded in 2015. We're quite a young company. We're growing aggressively over the last few years and soon to go public. So we've created a product line that has a number of technologies. We have our fiber machine that is going to be released next year. That will be covered in any other questions or another webinar at some other date. Studio system and shop system, both currently shipping. Studio system has been shipping now for approximately 18 months and is widely around the world. Shop system is just currently starting to ship and pushes us into different applications and technologies. The production system is the next stage where we move into mass production of metal parts, and that will be coming late 21. So on an agenda, we have the promise of 3D printing, how it works, and we're going to give you some case studies and application examples. So let's start with the promise of 3D printing. It comes from many manufacturers. It's a new-ish technology for manufacturing, which began for the request of rapid prototyping of certain components. So 3D printing delivers a promise of consolidation of parts, complex geometries that are either impossible to manufacture using current technologies, or we can use them to manipulate the 3D printing process and evaluate design and improve design. Design customization, so this is derived from consumer industry, where we have bespoke parts that are unable to be made using current manufacturing technologies. Rapid tooling, a way of creating tooling in a much faster way. On-demand manufacturing. As time goes by, this is going to become more important to the world economic climate, where we can call off a virtual library of parts and print on demand. This will lead us into the supply chain around the world, where we're not shipping parts, leading us to a greener world, more efficient world, and hopefully a better cost-effective part. So the first challenge we have is to deliver a product that is office friendly. We want to complete on-demand parts where we have no special facilities or highly trained operators, and we can deliver a broad palette of familiar materials. And this will lead us to a path of the mass production and the production unit, as mentioned earlier. So how it works, we'll start with the studio system. This product was designed with office friendly in mind, something that we can install on site quickly, easily, user friendly to use. So the user interface is simple and the equipment can be easily installed into most offices. So the idea of this process comes from metal injection molding. MIM is a powder metallurgical process, and it will enable complex shapes to be produced in mass production from inexpensive metal powders. It's been around a long while, and we've used that technology and developed it into our own. It's widely accepted and validated to ASTM and ISO standards and exists for a broad range of materials: stainless steel, alloy steels, copper, titanium, and cobalt-based alloys, etc. So MIM uses this sintering technology for many years with many powders. But how does MIM work? And how does it compare with our studio system? So let's start with MIM. So MIM uses a mix of metal powder and binder into a feedstock. You could say a slurry type form. This is then put into a piece of equipment similar to injection molding, which will require tooling, and the parts are injected and created so we can have a production level of parts coming off this machine. But we still need to remove the binder that is holding the parts together at this point. So we have to go into a solvent-based product to remove the binder that is holding the metal particles together. This is then taken in a raw state and placed into a furnace which densifies the metal particles and creates our solid part. So that's MIM, and that's the process of how MIM works. We've taken that technology and we've transformed it into a 3D printing technology. So where do we compare? So first of all, we look at the metal powder and binder that's used in MIM. We use a feedstock, which is very similar to what MIM is using. We combine metal particles of powder and binder together and create a feedstock rod. This feedstock rod is placed into a 3D printing machine, which enables us to print individual parts quickly and simply without the use of complicated and expensive tooling used for mass production. So we can produce a one-off part very quickly. But again, the same as MIM, we need to debind this part. We need to remove the binder from it, and we use a solvent in a piece of equipment that removes this. And then again, the same as MIM, we need to go straight into a furnace in order to densify the part and make it a solid piece of metal. So in order to do this, we have a three-dimensional printer, very similar to the FDM process or FFF process, and pretty similar to designs that you've used in the past over the last couple of decades that have come from plastic extrusion. So we've designed the printer to be office safe, to handle the material and the powder rods, so there's no powder handling whatsoever with regards in this process. Again, the debind is necessary to remove the binder. We've created a product that has low emission in design. It automatically distills the solvent inside, removing any binder or wax, and it's safe for an office environment. The furnace also, we've taken a lot of time and development to create one of the first office-friendly sintering furnaces. This will fit through a door and at its peak can reach 1400 degrees C. This is where we will place our parts and densify the powder particles into a solid metal shape. These metal shapes are what we call near net shapes. So the printer is capable of printing a part 12 inches by 8 inches by 8 inches, 300 by 200 by 200 millimeters. And the resolution and accuracy and surface finish is similar to casting. So we need to have the expectation of dimensional capabilities. At this point, it's geometry dependent, but we use a rule and a general direction of plus or minus 0.8%. Any critical dimensions that are needed can be achieved via a post-processing. For example, CNC, EDM, grinding, etc. Remember, this is a metal part. Whatever you could do before with a metal part, you can do now with this metal part. It's fully compatible with traditional finishing operations also. So if we need to polish, we can tumble, we can blast, we can plate it, we can even weld these parts together, and we can heat treat them. The example to the right here shows a part that's printed and sintered using a studio system, and it's compared with a cast part that was originally done. So we ask ourselves, what materials are available for the studio system? So at present we use 174pH stainless steel or 316L stainless steel. Recently we've released H13 tool steels and 4140 carbon low alloy steels. Soon to be released is copper, all being well this year, and sometime early next year we should be looking at releasing alloy 625 or Inconel based alloy powders. So let's just recap on the studio system. What are the advantages? No hazardous powders, no respirators, no dangerous lasers, no third-party equipment, turnkey, no dedicated operators, no welded supports, and no special facilities required. Every office would be glad to have this as part of their portfolio to use. So we're going to move on now to a more powder-based, our newest product in the portfolio of equipment to desktop metal. And how does a shop system work? So the screen in front shows you an example of the shop system printer, and on the right is the shop furnace. How does this work? So we look at the feed box. The feed box is full of powder. A roller will take a layer of this powder and put it into our build box. And the print head array will come across and print its two-dimensional geometry on that particular layer. The build box will lower, the feed box will raise another layer of powder, and the print head will print the second two-dimensional layer, eventually creating a three-dimensional part, which can be removed from the natural support of the powder and sintered. With this process, we don't need to debind through using a solvent, but there is still binder that's being applied to the part. We can thermally debind this through the furnace itself. This is an example of the ramp-up curve and the time for the sintering process to go through. So we ramp up, we thermally debind, we hold it for some hours, and then we ramp back up to somewhere around 1400 degrees where we sinter the parts together, and then we naturally cool down to create our solid part. So the shop system has some advantages that we can take to low volume or even high volume production. It's unparalleled productivity. Produce various parts, geometries simultaneously without the need of multiple setups. Produces hundreds of near net shape parts every day with dramatically reduced labour costs and expanded geometric flexibility. And as you can see from the example on the right hand side from a build box taken from the shop, you can see a number of parts, all different geometries, all built together in one go. This means we can pull from our virtual library and build at need. So as in MIM, we have a wide range of applications. And binder jetting can give you mass production, but without the tooling costs. These are some examples of some small components that we've successfully created and achieved. Some more examples here showing the quality and the detail that we can achieve with shop system. So I'm going to move into some applications and go through some case studies that we've done. But first, I'm just going to show you how desktop metal is growing around the world. This is a quick map of showing studio systems and where we've actually installed these systems and they're active today. These are the type of customers that we're selling to, and people that are using it in their design and application process. Some companies here where they're developing machine and tool design. So their challenge is to machine and tool design. If they have parts and they're low volume production, inexpensive mass production methods that require hard tooling are not possible. So, for instance, casting, metal injection molding, forging, stamping. Time is important to machine tool designers, and expense is important. So if we want to quickly test parts and move forward to create a better design, a faster design, and a more economical design, there's a need to test and iterate multiple complex geometries in parallel. Managing complex bill of materials and assembly procedures. So some machines need multiple complex parts all put together, built separately. Lead times, cost, all has an effect. This will lead to CNC shop bottlenecks, foundry lead times, non-reoccurring engineering costs. Fabrication of aftermarket replacement parts is also taken into consideration for break fix on their current machine tools. So where do we fit as additive manufacturing solutions? So for low volume production, we don't require tooling to use our process. And the part cost stays the same if you need one or you need 10,000. And we're capable of delivering that. So you need to test and iterate multiple complex geometries in parallel. Rapid prototyping parts in metal in the comfort of your own office. Test function under high load, heat and corrosion, and not just form fit. Managing complex bill of materials and assembling procedures. Using 3D printing, we can consolidate assemblies, allowing for greater reduced part counts and simplified assemblies. CNC shop bottlenecks. We can take manufacturing into your own hands and greatly accelerate manufacturing lead times. And fabrication of aftermarket replacement parts. So there's no need to keep parts in a warehouse for replacement parts. Just pull up the file, print, sinter, and ship the part in a few days. Some examples here you can see from a bearing housing, a planetary gear assembly, roller screw assembly, a small housing. The axle carrier and motor housing, bottom left, bottom right, are development from the fibre system using a tape. Again, we'll go into that on request. Herringbone gears, these are very complicated to produce and can be very easily produced in 3D printing. So I'm going to move into a motor mount. So tool design can be quite complicated and we need to reduce space, we need to reduce cost, and we may have to have many iterations of certain housings or mounts that we need to do. So this is an example of a standard NEMA motor that's going on a piece of equipment that requires lots of CNC setups. You have to send the requirement down to the shop and you have to wait for the billet to be machined, wait for space on the CNC machine. But during development, prototypes change and we can do this very quickly. And we also have lots of different sizes and geometries that we can produce. So for low volume manufacturing, less than 50 a year, on-demand printing eliminates CNC cost and inventory. part on the right is 3.5 inches by 3.4 by 1.9 for reference. And for reference at the bottom, we've done some calculations with outsourced CNC shop and what our cost would be against a studio system. First of all, you look at the cost. The cost is considerably less than CNC. What's probably more important is the lead time. We can create these parts in days rather than weeks. Next example here is custom mechanical coupling. Small component, quite complicated in geometry, but very easily done on a 3D printing metal machine. So this custom coupling for a rotary powered transfer between custom pieces of machinery, complex geometry to optimize power transfer. We've got the freedom of design here to transfer power in different ways than we could do when we had to machine these. Must be metal due to strength, stiffness, and lifetime requirements. So it's prototyped on the studio system, but would ideally be suited for mass production on the shop system. For reference, part 1, part 2, you can see a 1 inch by 0.9 by 1.6. And again, if we look at some outsourced costings that we have for CNC, the cost is considerably less, especially for low volume production. So a studio system can get you to the point where your design is correct, and then you can lock it down and build a low volume production run on a shop system. This particular one was costed at 750 sets per week. Another example here is a motion stage fixture or flexure. So this is to enable or to stop vibration. So this was designed and developed on the studio system. So a flexure is an engineering component designed to be compliant over a small range in a predictable manner. The flexure is used to allow the ball screw and motion stage to be slightly askew without binding or causing excessive wear. So complex geometry, thin wall makes machining, water jetting for instance, cutting particularly tricky and expensive. It'll enable to prototype at zero and zero in on the best design using the studio system. And then we can move forward again onto the shop system where we can low volume productions. Again, examples below and for reference sizes of the part. Roller screws, consolidated assemblies. This particular screw was actually originally built with 5 different components. These were merged together and built using a 3D printing process. It's 17.4 pH, and you can see the size reference is 4.8 by 1 by 1.5. And again, to actually CNC, this is very expensive. To actually use laser bed fusion is also expensive, but using a studio system is very inexpensive and also faster. Another example here is a bespoke worm gear speed reducer. Again, 17.4 stainless, and you can see this was compared with a current product, and we were able to do 72% lead time savings, and also, more importantly, a 95% cost saving. So custom brackets can be made out of metal, and they can also be made out of carbon, or being well with a fiber system next year using carbon tape. One bracket and a good case example, quite considerably shown in our website, is a company here where they have a 2001 BMW M3 and they want to fit it with a V8, but we need to use the existing mounting structure to hold the engine. So the guys here have reverse engineered this particular component. So they've scanned the existing one, implemented this into the fixing positions of where they need to be. Tested rapid design iterations using software, and being able to print a specific component that can hold a modern engine, V8 engine, in a BMW. And you can see from this example, two parts were created and welded together. This was then put into the car, and you can see the reasons why we wanted to ergonomically design this particular part to fit on the current test bed and the current setting of the engine mounting points of the car. It's very tight in there with the exhaust manifolds, but we still need the strength to hold the engine in the power. More example here of how tight it is inside the engine compartment. Another common example here where this technology is being used is very small sensor housings. So they're used to hold multiple sensors in precise locations to take machine measurements. Small features make it ideal for the shop system. Printing results in extreme reductions to both manufacturing lead time and part cost. Also allows for manufacturing flexibility. When the design needs to be modified to incorporate different sensors, engineers can simply send a revised file to the printer. And you can see the sort of productivity throughput of the machine for numbers of parts on the compared to the part shown here. 3D printing suits very well to complex gears. These are some very complicated gears to machine, but very simple to produce in a 3D printing process. Herringbone gears, mentioned earlier, very difficult to create. Very simple to create on a 3D printing process. Optimizing servo-driven timing belt pulley. So this was originally designed as a multiple number of components and was quite heavy and also needed to be balanced well on the machine for the timing belt. So the goal here was to build a less expensive to manufacture part, lighten the weight and lower the inertia to allow the servos to run faster. This again was done on the studio system. Very simple, work on CAD, work on design, and a very quick part was printed within a week and was actually assembled onto the machine. Bearing housings. Housings for press fit bearings needed to be produced quickly out of steel using the shop system. Required parts were printed in just one day and were ready for assembly in less than a week, requiring almost no operator labour. Printing on the shop system dramatically reduced manufacturing lead times for these parts compared to traditional manufacturing methods. Another case study that's come from the US is an assembly line ratchet tool, a very bespoke piece of equipment. The tool attaches to the machine in order to tighten and loosen socket head screws. This part requires metal for durability due to its repeated use. The customer is able to print this part with tight tolerances in a few days compared to weeks and weeks of machining, with a huge cost saving of 93%. Lead time saving of this particular part was 87%. Another application here in the boating world was a company called EWOL, founded in 97. So they're a leading vendor of high-tech marine propellers for sailing yachts. Stainless steel designs deliver performance, accuracy, and mechanical and corrosion resistance. So we haven't built the propeller itself, we've built the mechanism that drives it. So it's a pinion. It connects the propeller shaft to the blade. And you can see we have a part on the right-hand side here that is straight from sintering and has been fully machined to acquire the machining tolerances needed to go into the equipment. An example here on the left, this is a point where we need to start to understand the sintering process. So the sintering process needs to shrink during the furnace run. The part on the left-hand side is a fully sintered part from the furnace. The part on the right-hand side is a part just come from the printer itself. And you can see the difference in scale that we need to be. Some more high-resolution pictures of this particular component that has been machined. Remember, we're printing a metal component and sintering the part. So printing with a studio system was more responsive to the customer demands, a faster manufacturing process to reduce health hazards, less demanding in terms of logistics, no lot size constraints, lower part cost, improved part quality, and less labour intensive, and more sustainable than casting. So the business impact of the studio system had the ability to produce previously impossible geometries for improved performance, and it demonstrated the feasibility of additive manufacture as a manufacturing method, speed, flexibility, quality, and cost. So the next steps for this company is to explore AM for volume production with the shop system. The next company is a company from Italy, Cifarelli. Again, a very old company that's investing into additive manufacturing to develop its current products and develop into new ones. They're a leading vendor of architecture and gardening equipment. They have a rich history of technology and product innovation. Examples below some of the products that they deliver. So the challenge here was a shaker hook. So this is a piece of equipment on an engine that shakes a tree. It has 2,000 vibrations per minute and a stroke of 62 millimeters. So this SC800 shoulder carried shaker is ideal for harvesting nuts and olives. So the SC800 shaker can collect over 3,000 kilograms of olives per day, with a falling rate of 95% of the fruit, without damaging the tree or its buds. So the shaker hook becomes a very important key component, and the design impacts performance, reliability, and usability. So the company took this to optimize the shaker hook for custom applications. So the standard version produced by thousands in aluminium chill casting. So they want to do custom low volume applications requiring special topological optimization, geometries, and increased strength. So feature challenging weight constraints heavier hooks would be troublesome for both the operator and the gearbox on the engine that's driving it. So this custom shaker cannot be produced economically via aluminium casting and must be produced out of steel, staying within the weight and the bounding box constraints. The project's goal was to explore whether 3D printing is a viable option for customization of agricultural machines to reach niche applications and special spares replacement parts. Pictures on the right are the current part used. Company took it away under their own steam and redeveloped the head of this particular component and has fully tested it. So that brings that to the end of my session. I'm going to pass the ball back to Lucille and we'll be happy to answer any of your questions. Thank you very much for your attention.
Thank you so much, Kirk. That was a great explanation of the available systems, and I really like the examples and the applications you showed. I hope the attendees feel inspired right now, just like me. And I would like to mention some possible next steps here. You are very much welcome to get in touch with Layertec for a one-on-one meeting. We are happy to explore together how metal 3D printing can transform your business and which metal 3D printing systems may be the best fit. Also, we can perform a quick scan and assessment to provide you with some key metrics specifically for your organization. So feel free to reach out when you choose to visit us in our office in Zaltbommel. Then we can show lots of metal 3D printed examples and also the Desktop Metal Studio system. Otherwise, we are also happy to send over a free sample part. Well, let's check in on the Q&A if there are any questions. Let me check. I can see some. Let me see. All right. Well, this is then for Jeff, the other application engineer from Desktop Metal. How do you see the cost versus LBM? Similar, minus 20% or minus 50%? Jeff, can you provide an answer to this?
I do not have a good answer for this one. It's going to require a little bit more information. We are, of course, hoping to see a reduction in cost compared to LBM, but we would need a little bit more information to provide a better answer. I would recommend that you get in touch and we can look specifically at your specific scenario.
All right, that sounds good. Let me check if there are any other questions at the moment. I would say the presentation was quite clear. No other question at this moment to answer, so that's a short Q&A, but that doesn't matter, since when there are any questions coming up after the webinar or when you are viewing this recording, please let us know. We are happy to help out and answer those questions. So let us know when there are any questions at the later stage. To wrap up this webinar, I would like to highlight two upcoming webinars. The first one on December 1st and the second one on December 8th. First one is also with regard to Desktop Metal, 3D metal printing, and the second one is designing for additive manufacturing, which is focused on using the Formlabs SLA printer. So feel free to register on layertec.nl/webinars. And for now, on behalf of the Layertec team, on behalf of Kirk and Jeff as well, a big thank you for attending this webinar, and hope to see you soon again. Thank you. Bye-bye.
Thank you, everybody.